we should get started. So, you know, let me just say that you know, we had a couple of colloquia last semester, which were roughly on this topic of how do you architect you know, fault-tolerant qubits. So we had a colloquium by Michel Deboré from Yale on a bosonic error correction, and from Patrick Hayden on architecting a fault-tolerant qubit. And so, you know, I view this this colloquium today by Jeff Thompson in the same spirit of continuing this exploration. And so I should say, by way of introduction, that Jeff is he got his PhD with Misha Lukin, and he actually did his postdoc there at MIT and Harvard as well. He works on experimental atomic physics, and he's currently a professor in electrical and computer engineering at Princeton. But you know, I think he's been thinking in a very interesting, innovative direction about how you might you know, do error correction more robustly in atomic systems. We are converting general errors to erasure errors. So I'm really looking forward to this talk. It should be quite exciting. So Jeff, just turn it over to you.
Great, thank you very much. Just get my screen sharing going. All right. So it's a real pleasure for me to be here, and I'm very grateful to Umesh for the invitation. Let me, you know, say at the outset that, you know, I'm an experimentalist, and I normally give a talk that focuses on experimental work, but we have this this kind of more theoretical result recently that I think is interesting and is guiding the experiments we're doing now. And Umesh, you know, really encouraged me to focus this talk on that. So it's I'm a little bit out of my comfort talking, you know, mostly about theory. I'll discuss how exactly we're going to implement this in our experiments, and a little bit of background there towards the end of my talk. But you know, as a consequence, I'll probably say some things I'll probably say a lot of things that are very obvious. I'll probably say some things that are wrong, and I would love for you know, which ideas are which to be a topic of discussion at the end. But an overview of what I'll tell you about is, you know, I'll basically start with the claim that engineering qubits, physical qubits with favorable noise models can lead to significant improvements in, you know, either the fault tolerance threshold or the overhead that you would need to do fault tolerant quantum computing. And this is something people have been thinking about for a while in a variety of contexts. In this talk, what I'll tell you about is a kind of a way of engineering a noise model in neutral atom qubits, which are, I would say, an up and coming, but, you know, very exciting qubit platform that converts the dominant errors into erasure errors, which I'll argue are, you know, very favorable in terms of both threshold and overhead. I think this is probably, I'll sort of belabor the definition of erasure error and why it's beneficial, because I think probably these ideas can be extended to other qubit systems. We haven't exactly done that yet. And so for most of my talk, I'll be talking about this theory work in this paper here, which I want to, you know, emphasize was a really fun and unique collaboration with Shruti Puri and her student Yue Wu at Yale, you know, experts in error correction, and with another experimentalist, Kolkowitz, who also sort of, you know, was moonlighting as a theorist with me on this. But it was really, you know, this is really a unique collaboration to actually be able to think sort of deeply about, you know, what happens on the atomic physics side when errors occur, but also what the consequences would be on the error correction side. So I would, I guess, kind of describe in a nutshell what we're trying to do is cheat to win at error correction. You know, there's many, you know, for a long time thought about the thresholds and things like that for error correction in terms of a very idealized and, well, maybe not ideal, but abstract model of errors, which is just depolarizing noise. So X, Y, and Z errors, you know, are equally likely and act on the qubits in an independently random way. But if you have a simpler noise model than that, you can have much higher thresholds that are advantageous. And I think probably the most discussed example of this is biased noise, where, for example, say Z errors are much more likely than X or Y errors. And this case has been pretty well studied, and kind of a good code that you can use to take advantage of this is something called the tailored surface code. And it's been studied that for at least in the kind of quantum memory context, the threshold can actually be very high. In fact, in the case of infinite bias, the threshold can be 50% if you have this bias noise, whereas it's only 18% or so if you don't have any bias, if these errors are independent. But there's actually two kinds of threshold that are relevant for when we talk about codes and computing. The first is what I'll call the quantum memory threshold, where you imagine you have a code word with no errors, and then you sprinkle some errors in, and you get to do perfect, syndrome measurements and decoding operations. So this, with this kind of quantum memory threshold, the surface code threshold for unbiased noise, MWPM, is usually stated as 11%. Maybe ideally it's 18%, but it's in this context that you get this 50% for biased noise. But what is actually more relevant for real world quantum computation, but a little bit harder to compute, is what's called the circuit level threshold, where instead of just considering errors sprinkled into an ideal system that you have to then correct with ideal operations, you actually consider the circuit itself that you need to go and measure these operations and infer what errors happen and then implement the corrections in a noisy way. And these circuit level thresholds are probably always lower than these ideal memory thresholds. And for example, for the surface code, the standard surface code with unbiased noise, this circuit level threshold is around 1%. It's quite a bit lower. But it's this circuit level threshold that's really the thing that's relevant for fault tolerant quantum computing in a lab, because it's actually, noisy operations are actually the real world case that we have. And actually extending bias noise to the circuit level is a little bit tricky. So there's a lot of physical qubits that naturally have a bias towards one type of error or another. The rate of bit flips and phase flips is often described as T1 and T2 for qubits, and those are not necessarily the same in most qubit systems. But once you consider a circuit where you put all these elements, all these operations in, those gate operations actually mix up the errors. They convert Z errors into X errors and vice versa. And so that undoes the bias at a circuit level. So to maintain bias at the circuit level, the one thing that helps you do it is if you have something called a bias preserving gate, which is essentially a native gate that maintains the noise bias. And one really well-known example of this, and I would argue the only one that's been really extensively studied at the circuit level, is these kind of cat qubits, like the Kerr-cat qubit, for example, which my collaborator Shruti Puri at Yale did a lot of pioneering work in. And with these kinds of qubits, there's a technique that they proposed in this paper for actually implementing a bias-preserving C0 gate that maintains the Z bias of the noise even through the C0 gate. And with that, they're able to get an increase in the circuit level threshold compared to the case that you don't have this bias noise, or you don't use bias-preserving gates. And this increase in the threshold then means that for a given physical error rate, you obviously have much lower logical error rates. But even though we know of a lot of qubits that have this bias noise, we actually don't know of many where you can maintain that advantage at the circuit level. So another way that you can cheat, another type of noise model that's more favorable than just depolarizing errors, is erasure errors. And by way of explaining what this is, let me say that in general, the reason you get an improvement from these simplified noise models is that you reduce, when it comes time to decode what errors have occurred, you reduce the space of possibilities that the decoder has to distinguish between. And so if I had 5 qubits in sort of generic depolarizing noise, I have 15 errors I have to distinguish. If I had bias noise where I really only had Z errors with any probability, then I reduce the space to just 5 errors. But actually, if I have the error, if I somehow know independently from my syndrome measurement that it was qubit number 2 that had the error, then I've reduced it now to 3 possibilities. I have to fix the error on that qubit to detect which one it was, but I've reduced the space of possibilities. And so when we know the location of an error and can use it to facilitate decoding, that's, I think, what's meant by an erasure error. That's the essence of an erasure error. Erasure errors are actually pretty common. Like classically, for example, bad handwriting, you don't often read. Somebody tries to write an A, you don't often read it as a J, but instead you just say, I can't read what that letter is. And it's also actually, erasure has been pretty well studied in the quantum context, in the context of photonic qubits, because if I have a photon encoded, for example, or a qubit encoded, for example, in the polarization state or path of a photon, then I might expect a click in this detector if it's in the V state, a click in this detector if it's H. But if I don't get any clicks, then that is a third measurement outcome. That's an erasure error. It tells you there was an error on that qubit. And so because of this interest in photons, thresholds have been studied for erasure errors, and actually the surface code also, as a quantum memory, gives you a 50% threshold in the case that you have pure erasure errors. This was studied 10 years ago. So another way to understand why these erasure errors are more beneficial is that actually you just get a larger code distance for the same code. So in the depolarizing channel, if I consider this repetition code, distance 3 repetition code, I can detect up to 2 errors, but only correct one of them using majority vote. But if I have this erasure error where instead of 0 flipping to 1, both 0 and 1 become some other error state, and these actual error states don't even have to be the same, then I can actually detect in a distance 3 code up to 3 errors, and I can correct up to 2 of them. And so it's actually a generic property of any code, quantum or classical, in fact, that you can correct twice as many erasure errors as depolarizing errors. So this, if we could engineer physical qubits that would have a sort of a bias towards erasure type errors instead of depolarizing errors, we would expect them to be significantly easier to correct. So the context in which I'm going to discuss this is neutral atom qubits. And in atom qubits, and this also applies to ions, to first order, there aren't errors, right? These are basically non-interacting, perfect particles that sit floating in an ultra-high vacuum chamber, and the qubits might be encoded in, say, the 2 different spin sublevels of the electronic ground state. And to reasonable approximation, these states can have essentially infinite coherence time, but the challenge is that they don't. In that state where they have this infinite coherence time, they also don't interact with each other. So there's no 2-qubit gates, going on. And this is a classic trade-off with qubits. You have non-interacting qubits that live forever, but then you can't do gates, or you can have strongly interacting qubits, but then they decohere rapidly. So the thing that makes atoms and ions work really well then for quantum computing is that what you can do is use the fact that there's more than just 2 levels in this atom, and you can transiently couple the qubit to some other degree of freedom that is strongly interacting, and use that coupling transiently to implement a 2-qubit gate and then turn it off when you're done. So in the case of trapped ions, this sort of degree of freedom that you couple to transiently is the motion, the collective motion of the ion chains, the Cirac solar gate. And in neutral atoms, this degree of freedom that you couple to transiently is a highly excited state called a Rydberg state that's very strongly interacting. And I'll talk more about that on the next slide. But the challenge is that this other degree of freedom is typically, by virtue of being strongly interacting, typically a lot more sensitive to environmental noise and therefore much less coherent. And so it gives rise to errors. So the way errors crop up mainly in these atom and ion qubits is actually during a 2-qubit gate when you transiently couple to this, much noisier degree of freedom. And a consequence of this is that if you look at properties of atoms and ion qubits, you'll see that the 2-qubit gate error rate is typically 100 to 1,000 times worse than single qubit errors. So this is really the fundamental limitation. That's not to say that this is the only limitation, and actually a lot of, when it comes down to building these things, there's a lot of other sources of error like coherent errors, addressing, and crosstalk errors, things like that. But this, I think what I say here is sort of true about the fundamental limitations. So I want to, at this point, explain just a little bit to you about the Rydberg states that give rise to interactions that let us implement 2-qubit gates, because it's correcting errors from these Rydberg states that's going to be the key idea. So the energy levels of an atom, kind of no matter what atom it is, basically look like this. They're far apart near the bottom, and then they get really close together as you get to very high principal quantum number states again. And so our qubits are encoded down here, but these very highly excited states are called Rydberg states, and they have some universal properties that are important. The first is that the size of the electron wave function gets really big. So the ground state might be this big, but an n equals 50, which is not even a very big principal quantum number for us state, is orders of magnitude bigger. These can be almost micron-sized wave functions. And because these wave functions are so big, they're very polarizable, sort of fluffy. And so that gives rise to a van der Waals interaction where if 2 of these atoms are close to each other, they have an interaction whose strength grows as the 12th power of the principal quantum number. So if you go from n equals 5 to 50, you really switch on a very, almost pathologically strong interaction. And the lifetime of these states is not very long, but gets longer as you go up. So all of these things are favorable for implementing gates. And to give you kind of a sense of scale, if you have atoms that are a few 10 microns apart in a pretty high principal quantum number state, you can have interactions that are of order hundreds of megahertz and lifetimes that are hundreds of microseconds. So there's a favorable conditions for implementing high fidelity gates. So the way that we use this interaction to implement a gate is by coupling our qubit state into the Rydberg state. So I have these 2 ground states where I might store a qubit. It could be the atom could be a 0 state, it might be spin down, or the 1 state spin up. But then if I couple one of these states spin up to the Rydberg state, I can do something like do a 2 pi pulse and pick up a phase shift, a -1 here. And that would let me do a single qubit gate. But then if I have two atoms, I have to consider their collective dynamics. So if neither of them, if they're both in the 0 state, nothing happens. If only one of them is in the 1 state, then I can do a Rabi oscillation like this, just as if I had a single atom. But if they're both in the 1 state, then I'm trying to excite them both simultaneously to the Rydberg state. But the challenge is that I can't do that, actually, because the doubly excited state, because of this very strong Rydberg interaction, this Rydberg blockade, is shifted way out of resonance with my driving laser. This shift is much larger than my Rabi frequency. So then I won't actually do a Rabi oscillation all the way up here. I'll just have this constrained dynamics coupling from 1,1 to this symmetric W state, and that'll happen with a different Rabi frequency. So because the speed of my dynamics is different, 0, omega, and 2 omega in these different computational states, I can pick the right kind of pulse to implement a CZ gate, essentially using these different dynamics. And that's the basis of the Rydberg blockade gate. That's how this interaction is used to implement an effective 2-qubit gate between the ground state states. But the fundamental source of error, the challenge that we have to deal with, is that this Rydberg state has a long but not infinite lifetime, maybe a couple hundred microseconds. And so during the time that it takes me to do this gate, it has some probability of decay, and that's going to give an error. And for kind of current parameters for these gates, this is at the level of 1 to a few % error per 2-qubit gate. But an optimistic projection of where we could get by making these lasers faster and so on is maybe to about 1/10 of a percent. But this is the sort of the fundamental limitation to the fidelity. Now, the thing that's nice about atomic qubits, though, is that as a civilization, we're very good at atomic physics. We've been doing it for a long time, and so we really understand the physics of these things exactly, and also the physics of the error model exactly. So by thinking about what energy levels we use, we have some ability to shape and control what happens when these Rydberg states decay. The conceptually simplest model to set up would be one where when this Rydberg state decays, it can come back down to either the 0 state or the 1 state. And in that case, that would just give you a depolarizing error every time you had this decay. A cleverer thing that you could do would actually be to choose your spin states here, 0 and 1, such that maybe angular momentum selection rules forbid the decay from R down to 0. And so R is only allowed to decay to 1. And in that case, you would actually have a better error model than this depolarizing error because it would be biased. And the sort of reduction of these Rydberg decay errors to biased errors is actually the basis of a very, I think, important for us, important to set up how we thought about this problem paper from Misha Lukin's group on engineering error models in Rydberg atom qubits. But kind of the key idea of our work then is to try to take this engineering one step further. And instead of using, and actually what we do, instead of encoding qubits in the ground state, we encode them in sublevels of a metastable state, a state that doesn't have an infinite lifetime like the ground state, but still has a very, very long lifetime. It can be seconds in practice. But if we pick the right metastable state, then we can have the property that when we excite to the Rydberg state, if the Rydberg state decays, those decays overwhelmingly actually do not come back to this metastable state, but they go down to the true ground state, because in general, that's where atoms want to go when they decay. And I guess that statement, that's what atoms want to do, is not in line with the level of sophistication that I claim we have in understanding these atomic systems. But it wants to go back to the real ground state. And so if we then have a way to detect population that has fallen down into this ground state, and to do it in a way that doesn't disturb the qubits that are left up here, then we've basically converted these Rydberg decays into erasure errors. And I want to point out that there's actually a very analogous concept was proposed in trapped ions by Wes Campbell in this very nice paper. So if we want to propose sort of a physical system in which to implement this, there are two questions that are really critical. The first question is, what fraction of the errors actually become erasures like this? What fraction can you detect? This is equivalent to sort of asking what the magnitude of the noise bias is for biased polynomial errors. And then the second question is, can you actually detect them efficiently without disturbing the other qubits? If when you try to measure whether there were any erasures, you have some probability of inducing errors onto all these other qubits that didn't have errors, which is hopefully most of them, this might not actually be beneficial. So the central result of our work is to kind of think very carefully about the level structure of a specific atom, a terbium, and to show with sort of detailed atomic physics calculations that using this sort of triplet P0 metastable state, we can probably get to about a 98% fraction of errors converted into erasures, which is a very large bias towards erasures, and detect these erasures in a way that has negligible back action onto the rest of the qubits. It's a very efficient detection. So in the kind of the rest of this theory part of my talk, I'm going to explain how I'm going to take this result as a given and explain to you what the benefits are. And then in the last half of my talk, I will actually talk more about the specific atomic physics of ytterbium and how it is that we're able to do this. The picture that I have in my head actually for this sort of using these metastable qubits to detect errors is always somebody walking on a tightrope. And this, I guess, starts from a notion that maybe a quantum computation is a little bit like your qubits are a little bit like dancers. They're doing a dance. The dance is very intricate. They have to do all the moves exactly right. But the challenge with error correction is that you're actually not allowed to watch them do this dance. You just have to look at where they are, at the beginning and where they are at the end of the dance and infer whether they did all the dance steps correctly in the middle. So the notion of using this metastable state is somehow instead to ask these dancers to do their dance on a tightrope, way up 100 feet in the air. And the benefit of doing it this way is you don't actually have to watch the dancers to know that they're doing the dance correctly. All you have to do is look at the ground underneath the tightrope and observe if any dancers are falling down. And actually, you don't even necessarily have to watch in real time. You can just come periodically and check to see whether any errors occur. So by making the system sort of very unstable, very fragile, you sort of make these errors easier to detect. So in our work with Yue and Shimon and Shruti, we have this atomic physics model, and then the question is, how do you actually incorporate this into a circuit to see if you really get a circuit level advantage from doing this? And so we considered this specifically in the context of the XEZX surface code, and with the sort of the simplified error model, which I'll discuss extensions to at the end, where we assume there's only errors on 2-qubit gates because those are dominant for these atomic platforms. And we say every time you do a 2-qubit gate, there's a poly error with probability PP. And an erasure error with probability PE. And then the parameter that sort of governs how well this works is the erasure fraction, which is the fraction of all the errors that are erasure errors. And so in the circuit that measures the stabilizers, there's a series of 2-qubit gates. And after every 2-qubit gate, we illuminate the array with some light that would give off some fluorescence photons if any atoms had fallen down to the ground state, had these erasure errors. Although it's obviously not included to these stabilizer simulations, it's important that this is fast and you can do it in parallel across the array. But that's true for our scheme. And so then, most of the time, hopefully there's no error. But then when there is an error, we use a sort of a movable optical tweezer to replace atoms from a reservoir. And what this does is it converts this, this error that happened here, and this atom has actually been lost probably during our detection process, but we know there was an error there and we replace it with an atom. So this atom still, with respect to the code, it still has an error at some random state. And then we're going to use subsequent stabilizer measurements to sort of project it onto a specific error and correct it. But the important part is that because we saw this thing happen here and we know which atom we replaced, we know the location in the circuit of this error that we have to correct. And the way, so then in the circuit level simulation, we have to incorporate this information about where the errors are into the decoder. And this is conceptually pretty straightforward using the kind of matching decoders that you use for the surface code. So for normal depolarizing errors, if I have a string of say bit flip errors, then when I do my stabilizer measurements, I'm going to have 2 stabilizers at the end of that chain light up. And then the job of the matching decoder is to pair these up and infer, okay, there was a string of bit flip errors in between there. And if these errors happen near the boundary, then I can pair it to the boundary too, because the boundary qubits only have 1 stabilizer. But where the logical errors come from, the lowest weight thing that gives rise to a logical error is that if I have a string of bit flips that go halfway or more across my code, then for the matching decoder, it's actually fundamentally unclear whether it should kind of connect this to the left or to the right. And if it does it the wrong way, there's going to be a logical error. So with this erasure model, because I saw, at some point during my circuit evolution, I saw, qubit 4 and qubit 9 and qubit 73 lit up. I already kind of know which qubits have errors. So this makes the job of the matching decoder a lot easier, because if I now have this sort of d/2 set of errors, it kind of has some reason to believe that the qubits on this side, this glowing orb is supposed to mean that I knew that there was an error there. It knows which way to match it. And in fact, it not only can it do d/2, but it can do d-1. errors. And they don't actually all have to be erasures. If there's some errors that were sort of depolarizing errors that I didn't see in there, the knowing some amount of location information still lets me disambiguate. So it's actually very natural and straightforward to incorporate this information into the decoder, which is actually done by adjusting the weights in the decoding graph based on the locations of the errors. So in our simulations, which we actually did using the union find decoder, we find the following, that for this noise model of 2 qubit gates for pure depolarizing errors, you get a threshold a little under 1%, which is the sort of standard surface code number. But then by converting 98% of these errors into erasures, the threshold goes up by a factor of 4.4 to 4%. So this is a very significant increase in the threshold, which is sort of a benefit that you can spend in 2 ways, so to speak. You can either say for the same code distance and same physical error rate, I now have many orders of magnitude lower logical error probability, or if I have a target, say logical error rate, I can achieve that for the same physical error rate with a much smaller code. So say factor of 4, factor of 16 in the number of qubits that you need to use to reduce the overhead. I think actually the other benefit that maybe is the other threshold that changes that might even be more important for near-term work is I think we also talk about a pseudo threshold which is the threshold where your logical qubit performs better than just a single physical qubit if you try to use it. So this line here is that PL equals P. And actually this increases by a factor of 23 for a small code. So this big increase in the pseudo threshold may actually be really important for just near-term demonstrations of an advantage with fault-tolerant operation of a logical qubit in the first place. So in order to get this big gain, though, you need to actually convert a pretty large fraction of your errors into erasure errors. And we sort of looked at the threshold as a function of that fraction. We think we can get up here, but there's the whole curve. In the limit that you have pure erasure errors, you get to about 5.1% or something. So that's the saturated limit. This is a kind of similar to the curve that we saw for biased poly errors. And you can think of an eta sort of just like the biased px over pz over px as sort of related to this erasure fraction like this. And the behavior of this curve is actually pretty similar to biased polynoise, where you get about half the gain that you're going to get in threshold once this bias is 10, 90% here. And by the time you get to a bias of 100, which is 99% here, you've gotten most of the benefit that you're going to get. I'll point out that within this same model, and assuming bias preserving gates, we looked at bias noise, and this erasure, the threshold you would get in assuming only 2 qubit gate errors in the XEZX code for infinite bias is about 3.7%. So this erasure conversion performs comparably well, and maybe even a little bit better if this bias is really large. In addition to getting this larger threshold, there's another benefit, which is that you get a faster subthreshold decrease in the logical error rate. So the logical error rate below the threshold in a code is related to P over the threshold, and then to an exponent, which is sometimes called the error distance. It's the number of errors that the code can decode. And if we fix a code distance here, d equals 5, and increase this erasure fraction, what you see is that these lines get steeper. Basically, the error rate decreases faster below the threshold. And if we renormalize everything so that you can just look at the slopes, you see that it actually smoothly goes from an exponent of 3 to an exponent of 5. And then just extracting these exponents, you can plot that right here. So also, if you have a very high erasure fraction, not only do you have a much higher threshold, but you also have this faster subthreshold decrease. So these are two kind of distinct and complementary benefits. I will point out that as long as this erasure fraction is finite, there is some regime of sufficiently low error probability where you kind of go back to be dominated by the small fraction of depolarizing or poly errors that are left, and the slope does go back to d over 2. But you can't see it in this plot. It's at quite a low physical error rate. But the steeper slope doesn't continue forever. So that's the end of, I guess, the first part of my talk, discussing basically I guess why you would want to do this. What I have tried to explain is that this erasure-dominated noise model can give you actually a high circuit level advantage with the surface code that's comparable to or better than what you can get with bias noise. I think one question that is interesting is whether this is generic to other codes or just special to the surface code. The fact that codes have a larger distance for erasure errors is actually a generic property of code, so one would expect this is true. So I know people are really excited about things like LDPC codes and stuff like that. these days, I wonder if this could give a benefit for thresholds in that model as well. Another thing that we have thought about a little bit, but not considered extensively, is that the fact that you could also describe this erasure error as a gate with heralded errors. And in that case, if you think about resource or like magic state preparation in fault tolerant quantum computing, where you say prepare many noisy copies of a resource state and then distill out a better one, having a large bias towards erasure errors, which is the same thing as saying you can herald a lot of the errors, may actually allow you to do some kind of pre-distillation where you throw out copies of the state that had errors before you actually try to distill them. And this might also give you a significant reduction in the overhead that you need for doing universal fault tolerant quantum, because this resource state preparation is a very large fraction of the qubits involved in a computation in these kind of resource estimates that people have done for Shor's algorithm or things like that in the practical regime. So in the next part of my talk, then what I'll do is dive a little bit deeper into the physics of neutral atom quantum computing and also introduce that topic in general a little bit, and then how we use kind of a specific encoding in a terbium to get this error model with a large bias towards erasure errors. So neutral atom quantum computing, in the kind of schematic diagram that you need to have in a nutshell is that there's a ultra high vacuum chamber where an array of sort of tightly focused laser beams called optical tweezers holds an array of atoms. And each atom is one qubit, encoded in the spin, as we previously discussed. You can, you measure these atoms by using fluorescence on a camera. You control gates and the execution of the circuit using light by focusing down laser beams that drive particular transitions in the atom onto this array. And then the interactions between the atoms are realized using these highly excited states called Rydberg states, but when they're in the ground state, they're very knowing they're active. This field has, I think, really taken off in the last couple of years. There's now at least 25 academic groups, and I put 25 plus here because I got tired of counting, but it could even be a larger number than this. And also, really exciting for me is 4 companies at least working in this area, including Kolkowitz, Atom Computing, Clara, and Pascal. And one of the things that's really exciting about this neutral atom technology is that it kind of comes with at least some first level of scale built into it. It's already pretty clear how to make pretty big arrays of qubits. This is from Misha Lukin's group, a 16 by 16 array of atoms, 256 qubits. And the technology for going even an order of magnitude or so higher than this is already sort of pretty clear, because there's just using photonics for the addressing and control really gives you a lot of parallel kind of control built in. It's a little bit different from superconducting qubits, for example, where 2,000 qubits means 2,000 or 4,000 or 6,000 wires, for example. So there's a couple of key ingredients that go into this neutral atom computing. One is that you can actually not only make sort of arbitrary arrays of traps, but also move them around in real time. And this is used to create defect freeze arrays as the starting point for these computations, which you can do in 1D, 2D, or even 3D. But the fact that you can move these atoms around is also important for this step in our erasure protocol where you need to replace lost atoms by moving new atoms in from the serial. So I already mentioned the properties of these Rydberg states. So I'll just remind you briefly that these highly excited states give you these strong interactions. And the way in which we normally talk about this interactions is the Rydberg blockade, where if I have an isolated atom, I can just excite it to the Rydberg state. But if I bring it close to another atom that's already in the Rydberg state, then that excitation is forbidden. And so the way in which the new point I want to make on this slide is that the way we quantify this is with something called a blockade radius, which is the separation between atoms under which you cannot excite two of them. And this is related to the principal quantum number at your driving strength. But for kind of typical parameters, this blockade radius is maybe about 10 microns, whereas spacing that you can engineer between optical tweezers is something maybe between 2 and 5 microns. So this is these length scales work out really nicely with respect to each other, because on the one hand, this blockade radius isn't infinity, so you can actually implement gates in parallel across your array. I can excite an atom here to do a gate over here, and the same thing over here. But at the same time, it's large enough that it comfortably covers two or maybe even 3 lattice sites. So you have some kind of flexible local connectivity. And then to extend this blockade to generating gates between qubits. We just need a selective excitation of one of the qubit states to the Rydberg states. And I'm going to kind of flip through this because I already introduced this. But then let me point out that kind of the current record fidelity is around the 98% level. And this was, this level was first achieved by Misha Lukin's group a few years ago, but has now been matched by I think at least 2 other groups, if maybe not in published data, in exciting unpublished work that there are rumors about. And then it's actually an exciting week for this field because last week in Nature, I should have updated both of these citations, but these papers were both in Nature last week. Both Misha Lukin's group and Mark Saffman's group demonstrated, what I would call the first kind of, fully featured programmable processors based on neutral atom qubits. What's really interesting to me about these papers is that they have very different approaches to do that, which illustrates there's still a lot of room for creativity and innovation in this neutral atom space. In the paper from Misha Lukin's group, they implemented the programming not actually by focusing light onto different sites, but by actually moving the atoms with respect to each other to change their connectivity. So just bringing atoms close together when they should do a 2-qubit gate, moving them far apart when they should not. Whereas in Mark Saffman's approach, they did the thing that was maybe originally envisioned, which is actually focusing the excitation lasers down and saying, okay, I'm going to excite this qubit, then this one and this one, and programming the circuit that way. And the fact that groups like Misha's and Mark's and also Antoine Brouet's, who have been sort of pioneers in this neutral atom Rydberg space, are now doing such big and impressive circuits with these qubits, with these neutral atom qubits, is I think really exciting for the field, but is also kind of created the space in which the work that I'm telling you about here makes sense, where now I would say the fundamental fact that maybe neutral atoms are interesting is really well established by these guys. So I would describe the work I'm telling you about here as kind of going back to the drawing board and thinking about what would generation 2 neutral atom qubits like. That work wouldn't be possible without generation 1 being pretty firmly established.
Quick question, Jeff, about
yes, Umesh.
About these 2 results that you just mentioned. So are the gates applied sequentially or in parallel on these qubits? In Misha's case, they are applied in parallel to some extent. So there's but I think they're basically applied in parallel. So there's a 2-qubit gate happening here and here at the same time. And then the connectivity switches, and then the gates are done in parallel. With this scheme, they certainly could be done in parallel if the addressing system allows it. I don't actually know if they were, but Mark is here.
I can just say that 2-qubit gates were done sequentially. There are parallel 1-qubit gate operations.
But I think the fact that they were not done in parallel is a question of not of physics, but of physics of neutral atom qubits, but of physics of these modulators here. Okay. So for our kind of attempt to find 2nd generation qubits, we went back to the drawing board, and the drawing board for atomic physicists is the periodic table. All the experiments I showed you, and in fact, most of the experiments that have been done with atoms of any kind, VCs, whatever, have been done with alkali atoms from the first row of the periodic table because they look like hydrogen, and hydrogen, we understand it very well. But kind of the Wild West, so to speak, or maybe this is more like Chicago actually now, but the Midwest for atom qubits is now these alkaline earth atoms, which have two electrons. They look a little bit like helium. And they have just a slightly more complicated level structure that gives you a lot of additional features that you can use. And so the work in my lab that we've been doing is using a terbium, where the particular reason we're drawn to a terbium out of these is it's the only one with a spin 1/2 nucleus, which is a really natural way to encode this qubit. There's also been a lot of really exciting work in strontium, which is maybe the better developed one of these. And really exciting work on quantum simulation, kind of many-body dynamics, and also atomic clocks. It is, however, very difficult to encode qubits in strontium because the only nuclear spin is a very large spin, and so it's difficult to isolate a 2-level system. I kind of started working on this about the same time as Adam Kaufman and Manuel Endres at Gila and Caltech, respectively. And I think this field of looking at alkaline earth atoms for neutral atom quantum computing is now also taking off, in its own right, sort of mirroring the trajectory of neutral atoms as a whole. And there's, at least a dozen or so experiments around the world, also being built now using these atomic species. I don't want to be too technical, but let me just give you kind of an overview of what features we get from this level structure. The fact that there's 2 electrons gives you singlet and triplet states, and now you have allowed transitions conserving the spin and weak transitions flipping the spin, which is really advantageous for laser cooling. In the ground state, there's no electronic spin, so nuclear spin, the qubit, if you have a nuclear spin, should have essentially infinite coherence. There's also this highly forbidden optical transition, which is the basis of optical atomic flux, which I think will someday redefine the SI second, but for our purpose, just gives you another way to encode a qubit. And in fact, you can use this nuclear spin in this metastable qubit as well. In this metastable electronic state as well. It also has no electronic angular momentum. And then the other feature is that within this ytterbium atom, we have an ytterbium ion inside the core, and manipulating the optical transitions of that ion within the Rydberg atom has turned out to be maybe the most useful feature that's particularly important for these error correction ideas. So I don't claim to have explained all of these things in enough detail to understand them, especially maybe for this more theoretically inclined audience. But maybe the metaphor that I want to have here is that these this is our toolkit, and these alkaline earth atoms are really like a Swiss Army knife, where they have all kinds of weird and potentially dangerous appendages on them. And what we've been doing for the last few years is basically trying to figure out if we can do anything useful with any of these. This error correction work is one thing in that category. So over the last few years in my group, we've kind of learned how to cool and trap ytterbium atoms and optical tweezers, done a lot of, I would say, foundational work, like measuring where the Rydberg states are and verifying that they have strong interactions, both of which were not really known before our work. And then in very recent work, we've actually implemented finally a full set of qubit operations in these atoms. And actually our paper demonstrating a universal set of gate operations in the 171 ytterbium just came out in PRX a couple hours ago, accompanied by a paper from Adam Kaufman's group with doing very similar work in the same species. Just to kind of flash up, the fact that these qubits work, we do have a pretty typical set of tricks for initializing the qubit into one of these spin states, for example, using optical pumping. And then we use, in our case, a global RF field to drive Rabi oscillations to do single qubit gate rotations between these and get nice oscillations. In our work, this is done globally. We have only global addressing for single qubit gates at the moment using RF, but Adam Kaufman's groups demonstrated optical Raman gates also with global addressing, but the path to implementing them on the single side is clear using their approach. And these single qubit gates work well. The single qubit randomized benchmarking fidelity is high, which it should be for just doing Rabi oscillations on a spin. We implement 2 qubit gates using the approach that I described, where we excite them to the Rydberg state. The thing that's a little bit funny for the experts in the audience about how we do these Rydberg gates is that the selective coupling of just one of the qubit levels to the Rydberg state is achieved actually not using selection rules or energy splitting in the ground states, which are almost degenerate, but actually using a Zeeman splitting in the excited state. So in the Rydberg state. So the reason only one goes to the Rydberg state is because of the splitting up here. And we use this gate protocol that from Misha Lukin's group that I described earlier to implement our 2 qubit gates, and we get reasonably okay performance for the very first demonstration of a 2 qubit gate in an alkaline earth atom. It's about 83% 2 qubit fidelity after we do spam correction. We understand this to be limited primarily by technical noise and laser noise. Our laser system was not especially optimized to do this particular gate, but it's sort of an existence proof that you at least can do gates in this atom. So what we're working on now is promoting, instead of encoding qubits in this ground state, encoding qubits in this metastable state. Part of the motivation for doing that is this error correction work I described, but the other reason that we were already working on this is actually that this is just a better state to do gates from in the first place, because we can get much faster excitation to the Rydberg state starting from this state using only a single photon transition instead of having to use a 2 photon transition from the ground state. So this is already a really good idea from the perspective of this atomic physics. And we actually think we should be able to do our gates, maybe somewhere between 10 and 20 times faster starting from this state, which should actually give us a 10 to 20 squared times improvement in technical noise, which is what we're counting on to get these gates better. Using the metastable state also actually lets you do mid-circuit measurement very well in a way that I won't talk about today. So having introduced kind of a little bit about these neutral atom qubits, and in particular ytterbium, then let me tell you how we in the context of the specific energy levels here, can implement this error model or a qubit encoding that gives rise to this error model where we have primarily detectable erasure errors. So our qubit, I guess in an abstract sense, as I drew earlier, you have 2 ground states that store your qubit, and then the Rydberg state decays and gives rise to errors. But now we use a metastable state, not the ground state, to encode this qubit, and it's the triplet P0 state, which in ytterbium has a lifetime of 20 seconds. So it's a very long-lived state, even though it's not infinite. So now let's kind of account for where the errors from this state go. So it turns out, and these numbers come from just atomic physics, the matrix elements that we pretty much know for ytterbium. 34% of the errors are actually going to come back down to the real atomic ground state. And when they do, we can detect them by using fluorescence on this singlet S0 to singlet P1 transition, which is a closed cycling transition, has negligible probability of decaying into these qubit states. And also this light is not resonant with any transitions starting from this state. So applying this light is both not going to put these qubits back into the computational space, but is also not going to kick any more qubits out of the computational space. So being able to efficiently detect these converts these decays into erasure errors. Another big chunk, almost 2/3 of the sort of decays from this Rydberg state aren't actually really spontaneous decays at all, but they're black body photon-induced transitions to other Rydberg states. Up to these very high principal quantum numbers, you have kind of microwave frequency transitions between states, and those can be driven by thermal radiation. And these we can detect by converting them after a gate. We can apply a pulse of light that's resonant with the ytterbium plus transition inside the core of this atom, and that, through a process called autoionization, within like 100 picoseconds, creates an ytterbium plus ion. And that ytterbium plus ion, we can also detect with fluorescence on its cycling transition, which also is not going to disturb qubits in this state because this light is also very far detuned from transitions from here. These ions are not trapped, so it's a little bit harder to detect them, but we think with very realistic parameters, this can be done with at least 99% fidelity. And then these also become erasure errors. I'll also point out that this autoionization process doesn't actually care about which Rydberg state you are in. It detects both these other Rydberg states that can be populated by blackbody transitions, but also this original Rydberg state here. So you also catch any leakage from the gate into this state with this approach. So then in the end, only 5% of the errors decay back to this computational space where they could cause qubit errors. So basically with this encoding, and given the way these energy levels or these matrix elements work out in ytterbium, we've engineered a qubit that has a really high fraction of errors as these erasure errors. The reason this works well, so to understand kind of quantitatively how this, where these numbers come from, I've first plotted here just the branching ratios of where it decays from a particular Rydberg state. I think this is 75S, 3S1. And what you see is that, about most of the errors, about 2/3 of the errors are black body, 1/3 are radiative, but among these radiative errors, various selection rules tend to favor higher J states and whatnot, such that actually the fraction of these decays that go back to the qubit subspaces 3p0 is just very small. And this is just a combination of all these selection rules and angular momentum tendencies. But actually there's another, so it's only 5, if once you include the multi-photon decays from these states, it's 5% that come back to 3p0. But it actually turns out that if those decays happen in the middle of the gate, they have a relatively high probability, 70%, of being re-excited to the Rydberg state by the rest of the gate, because our laser is still on. And those re-excited qubits also are converted into ions at the end and detected as erasures. So when you kind of multiply this 5%, 70% together, then it actually in the end is only 2% of errors that are end up back in the qubit space, or another way is that 98% of the errors decays become erasures.
Sorry, can I ask you a naive question here?
Yes, please.
So is there one relevant number or two? One relevant number seems to be what percentage go back to the qubit space, and then is there a different number which is what percentage do you actually detect, and is there a middle number, and how do you think of that one? Yeah, so
well, there's what percentage go, well, okay, I would say there's what percentage go back to the qubit space and what percentage don't, and those add up to 1. But then the ones that don't go back to your qubit space are, they're definitely kind of lost from your computation. So then if you can detect them, it's very beneficial that they're these erasures, but it's not necessarily the case that you detect all of them, right? So there's a question, what is the detection fidelity for those atoms that leave the qubit space, when there's an error. And we think that, detecting atoms with single atoms are actually quite bright in terms of fluorescence. So for these ground state atoms, we're quite confident that we can do this at the 3 nines level. For these ions, I think 2 nines is a more realistic estimate. So there is a question which we have not actually analyzed in detail of what is the impact of missing a small fraction of these events. That is a separate number.
And sorry, just following up on that a little bit. So the ones that were lost, did not go back to the computational space, but and you did not detect them. So now there would be a missing qubit there. So how does that affect the subsequent computation?
Yeah, so and atoms can get lost for other reasons too. They can get knocked out of the trap by background gas, or they can just fall out of the trap for other reasons. So it's not an error that's of a kind that's fundamentally distinct from errors that you would have to deal with to be, rigorously fault tolerant anyways. So there are, but this is more like kind of a classic leakage error. So I think there's a lot of proposals. Mark has a review paper from 2016 where he proposes this sort of knock-knock protocol from Preskill to deal with this. I think there are actually probably more clever schemes to deal with this more efficiently, like in the surface code. And I think at the end of our paper, we cite a paper from Suchara, Cross, and Gambetta from IBM on this sort of quick leakage reduction circuit that actually seems like it should work with pretty minimal impact on the overhead, where you basically swap the data in the ancilla qubits after every cycle to try to detect, and since you detect the ancilla every time, you can tell if it's missing. But we have not analyzed that quantitatively, but I think it's not going to be a big deal if it's rare.
There's also a question in the chat from Liang. Do you want to ask that directly, Liang?
Yeah.
Yeah, so the question is, will there be back-hashing error even if there's no leakage events?
So what do you mean
So it's like if you don't detect a leakage, it's more likely it will be in the 0 state.
Yeah, so that's on my, I think that comes up in one slide.
Okay, thanks.
So yeah. On this slide, exactly. So this 98% comes from some kind of analytic calculation, but to sort of validate this understanding, we also did master equation simulations of the full 2-qubit gate, and what we see is that the sort of the total, the average gate fidelity gets better as you do your gates faster and faster. But then if you condition on not detecting one of these leakage events, then it's better by a factor of 50 still. And this 50 is this 98% cast in the inverse. It's 1 over 2%. So you get a big conditional improvement in the fidelity, but by not having an erasure error, but there's still some small probability of an error. But this actually consists of 2 parts. One is the error from decays, back down into the qubit subspace, which can cause, reveals information to the environment about what the state of the qubit is now. But also the fact that you didn't have an error gives you this kind of no jump evolution, which is what I think you were asking about, Liang. That even if you keep running gates over and over and you never see any erasure errors, that eventually tells you that your qubits have to be in the 0 state, because if the 1 state is the only one that goes to the Rydberg state, there should have been an error eventually. In terms of this average gate fidelity, this is quadratic with the error probability. So in the regime you want to be in, it's conditionally very small. But it's an interesting question of whether this, because it's a coherent error, whether it actually really, whether this average gate fidelity that's quadratic is actually the right measure for thinking about these error correcting codes. And that's something I'd be happy to discuss later. The other thing that's important, though, that in this simulation is there's actually different kinds of signals you can get for detecting errors. The atoms can, one can go down to the ground state, one can become an ion, they can both get down to the ground state. And we can detect most of those, but if both atoms in a 2-qubit gate become ions at the end of the gate, then that we actually can't detect, because if you create those 2 ions within a few microns of each other, they just blow each other. The repulsive force between them is so strong that they'll leave before we can detect them. But one thing that was kind of a nice surprise, I can't really say that we designed it, is that the probability of creating the kind of error that gives you 2 ions is very strongly suppressed by the Rydberg blockade. It's actually an even stronger blockade than the normal blockade that suppresses those type of events from happening. So the probability of those things happening is suppressed by many 4 or 5 orders of magnitude compared to the errors that we're mainly worried about detecting. So that was a pleasant surprise. So I have only one more point I want to make, which is that, all of this discussion so far has been about only 2-qubit errors and only 2-qubit errors arising from the finite lifetime of the Rydberg state. And I don't think this is like completely irrelevant, because that is the only fundamental limitation of the fidelity freeze. But there are other errors that, for sort of technical reasons, which can be as insurmountable as physics in some cases, there's other errors that happen. And what about those? What's our budget for those? Or do we have to worry about those eroding our advantage here? And so the one type of error that we studied in our paper is initialization and measurement errors. And we have a pretty good handle, in our system and in other neutral atom systems, this can be done at the sort of 99% level. And just by inserting those into our circuit level simulations, what we found is that they have actually pretty minimal impact. The solid lines show the kind of the logical error rate for 0% for no initialization and measurement errors, and the dashed lines are 0.5%, which is reflective of some state-of-the-art value. And these don't matter very much, and that's consistent with other simulations of the surface code, that those kinds of errors are way less important than 2-qubit gate errors. But there's other types of errors that we haven't considered in detail, but I want to just kind of lay out our thinking about them, maybe spark some conversations. The first is that, the new error that we've introduced by going to this metastable state is that we have to worry about the finite lifetime of that state. It can decay. In the ground state, we would have had an almost infinitely lived qubit. Now we have this finite lifetime. This one I really don't think matters very much, because what happens when it decays, it goes to the ground state, and that's an erasure error. So I think to the extent that these erasure, and it's just a single qubit erasure error, and we'll detect it with our normal protocols. So this one is I think is not going to matter at all. There's also an issue of doing, locally addressed single qubit gates using Raman transitions. The level diagram looks similar to these Rydberg states, but you're not going to very highly excited states. And here, I think it's likely that you'll have essentially a similar fraction of conversion into erasure errors from these, because the selection rules coming from these intermediate excited states are similar to the Rydberg states. But the one that's more important is coherent errors. So, lasers are noisy, atoms move around, and that gives rise to Doppler shifts. And this can cause problems for both single and 2-qubit gates. And these are actually in current implementations, among the dominant errors. And I think the same thing actually applies for ion traps. And here, the vision that we have for how to handle these, which is sort of an open research question for us right now, theoretically and experimentally, is to use a technique known as composite pulse sequences to drive these gates. And the idea is that instead of, say, doing a single 2-pi pulse to the Rydberg state and back, you actually do a series of maybe pi pulses or pi over 3 pulses, or maybe some optimal control drive sequence, which executes some more complicated and longer trajectory. You spend more time in this Rydberg state on average, but does it in a way that the fidelity of the final gate is robust to like a higher order against errors in the parameters, like, for example, the Rabi frequency of the laser or the detuning of the laser. And so what these composite pulse sequences let you do is trade robustness against rotation errors for a longer sequence. Basically trade coherent errors for spontaneous errors, which would arise from the longer sequence. So actually my understanding is that in trapped ion qubits, there's been a lot of work on these kinds of gates, but they have not actually realized a significant benefit in practice, because the fact that you make these things longer increases the gate error rate from motional heating and things like that. So it ends up being a wash, basically, whether you do this or not. But in our case, because we have this conversion of spontaneous decay errors from the Rydberg state into erasure errors, we would actually much prefer to trade rotation errors for that. So I think this might create a new perspective and a new argument for the use of these kinds of pulses. But we're actually trying to understand how well these work for Rydberg states now. But maybe the final thought here is that, you actually have to, if you want to have this very advantageous noise model, you have to consider not only the error you want to, but actually all the operations, and think carefully about them to maintain this significant bias towards erasure errors. So I guess maybe have two very thin concluding remarks here. The first is that, the fact that this works in this atomic species 171 ytterbium actually kind of involves a number of what appear to be miracles about, how these atomic properties work out, which is really unique and nice. And the second is that this project that we embarked on with Shruti of really trying to and Shimon and Yue of really trying to co-design a physical qubit encoding and an error correction code was actually very difficult at first to really learn to speak each other's language, but I think was very productive in the end and very exciting. And I think that this kind of work is this system level thinking is something that I hope can be reproduced across the field. So with that, I'd like to I thanked my theory collaborators at the beginning. I'd like to thank my students who actually did this experimental work here at the end of our talk. Here's a picture of a neutral atom quantum computer. And then also thank you for your attention.
Great, thank you, Jeff. That was a beautiful talk. It's a real, for speaking as a theoretician, it was a real window into the experimental way of thinking about things, as well as really beautiful ideas. So let's see if there are any other quick questions before we move on to the panel. Hi, Manuel.
Hey, Jeff. Beautiful talk, really great results. I'm wondering, and there's nothing that prevents me from doing this in analog quantum simulation as well, right? I mean, I could say if I have just an encoding from a metastable to a Rydberg state, detect these kinds of errors the same way, and try to enhance my fidelity by just post-selection.
Yes, I think post-selection would definitely work for you. I think the challenge, the thing that's a little more favorable about circuit model computing is that we bring all of our population back down from the Rydberg state periodically during the computation, and that gives us a chance to create and clear out these ions. I think at least in the experiment, in these kind of quench experiments where you're doing now, you want to have a large circuit depth, but that's kind of continuous evolution, including the Rydberg states. And if you make any ions or anything like that in the middle, you're totally screwed. But post-selection, at least, you could figure out after the fact if it happened. So like a heralded thing, you could definitely do.
Yeah, I wonder about similar questions for coherent errors, because I mean, some of the laser errors you can classically detect, I believe, right? Say if you have amplitude noise, specifically for Rydberg, say intensity noise is extremely hard to stabilize because it's so fast. But say you have extremely good photodiode, you know what it is, right? So you could post-select like that and detect it. Maybe you could also select it with like a bunch of kind of ancilla atoms that would see it or something like this. I think there might be something like that. It might not be 100%, but maybe you get another 10 or 20% like that.
I think those are really interesting ideas. Yeah.
Umesh, I think you're muted.
Sorry, Steve, you have a question?
Hi, yeah, thanks for the wonderful talk. So you did your work with the XEZX code. Do you know if there's any real reason why that's a good code to use in the context of Erasure, or if other codes might perform similarly?
I have asked that question to Shruti as well, and I think the answer is no. There's no reason to believe that it would work better. I think they were already working with it in the context of their bias noise stuff and had all the infrastructure set up. But
Thanks.
Is there any other question before we move on to the panel? Okay, so Jeff, if you could stop sharing your slides, then we could maybe get the panelist videos pinned. Okay, in the meantime, there's a question in the chat. Is there any benefit of continuous illumination where errors would appear stochastically, but immediately?
I see. So if I illuminate, instead of pulsing on the illumination to detect these errors at the end of a gate, I keep it on continuously to try to detect, exactly the moment of the gate that it occurs. It's hard for me to think about what the benefit of that would be, because I think at the end of the day, the qubit is depolarized, basically. I mean, you could maybe argue that if you saw that the error happened, in the first 10% of a 2-qubit gate, then you sort of know that the error probability is very small. But that's a very small amount of additional information, and I don't know. It's an interesting idea, though.
Okay, great. Can we get the panelist videos? Okay, great, perfect. So let me start introducing the panelists. We have a really fantastic panel today. We have Ken Brown from Duke University. He's actually a professor in ECE physics and chemistry, and he works on quantum computer architecture, on quantum control, and of course quantum error correcting code. So very appropriate for this particular topic. There's Ignacio Cirac, who is at the Max Planck Institute. Ignacio is a theorist who works broadly on everything you've probably heard of, seen him here on panels before. But for our particular talk today, I think what's interesting is that many of the original proposals, experimental proposals for experimental quantum computing came from Ignacio in his work with Peter Zoller. So great to have you here. We have Liang Zhang, who's on the faculty at Chicago. He's a theorist, and he works on sensing, communication, quantum computation, but with, again, a special emphasis on quantum error correction, which is, so welcome, Liang. And then Mark Saffman from Wisconsin, who's an experimental atomic physicist. And Jeff already spoke about how important his experiments are to setting up the foundations of what Jeff has been talking about. So, it would be good to start with the reactions of the panelists to what was to Jeff's talk. Maybe in some order. Maybe Ignacio, do you want to start?
Yes, of course. Well, first of all, thank you very much for this beautiful talk. It was, I think, very clear for everybody, physicists, computer scientists, at this part of the talk. And I think it's a very nice idea, very good idea. And I think that it is needed at the moment. So it's methods to trying to scale up our systems and reduce the errors. And in that sense, I mean, the way I understood it, I think it's a good idea that has a practical application. I mean, I have some questions, maybe are not so urgent. I don't know if I should ask them now or later on.
Yeah, sure, why not? Yes, please do.
Yeah, so my question is about time scales. So somehow, maybe I'm not up to date, but I thought the Rydberg gates are very interesting because they can be very fast as compared to some other gates like collisions. They have other let's say advantages, but that's one of them. And however, I guess that when you start to measure and do the measurements and wait until you have the result in order to act, and in particular, in the case that you would lose the atoms and they go away, you have to replace them, then this will take some time. And so I'm wondering to what extent this diminishes some of the advantages that the Rydbergs have, or if it's something that is independent.
Should I answer that? Yeah. So yeah, that's a good question. And in fact, when we showed a draft of this paper to Mark Saffman, that was also his first question. And as a result, I think it's like supplementary section S27 or whatever has a little bit of a sketch of this. But I think the essence of it is though that the Rydberg gates are very fast, maybe a few hundred nanoseconds. But this erasure detection, because you're not trying to keep the atoms, we do this detection so we just blast the atoms with resonant light. That actually can also be very fast, just at the level of a few microseconds. Is how long that would take, because these are strong transitions. That's very different from the current state of the art from, say, doing a measurement of an ancilla qubit where you want to measure what its spin state is, but you also want to keep the atom so you can reuse that ancilla qubit. In current implementations, that's, depending on the system, somewhere between like 20 and 100 milliseconds. So that's actually very slow, orders of magnitude slow. So what we work out in the supplement to our paper is that if when you get to measure the ancillas, which you do less frequently than we stabilize your measurements, you have to do this slow readout with current technology, then all this erasure stuff isn't going to change the cycle time at all. And that in order for it to become the limit to the cycle time, you would have to speed up that ancilla measurement by about 2 orders of magnitude. So this is a known problem and people are working on it. The other operation in here that's not that fast is replacing the atoms, but I think that's not going to turn out to be a big limitation because you don't have to do it right away. In the circuit that I drew, we did it right away, but there's certainly no point in doing it until at least you finish the next round of stabilizer measurements. So you can actually batch a number of these atom replacements and do them at the same time. And the work of Misha and others has shown that parallel atom moves are essentially free compared to single atom moves, because it's just the acceleration time of some whole pattern. So I'm also pretty optimistic that that's not going to affect the operation time.
Okay, thanks.
Thanks, Ignacio. So who would like to go next?
I can go next.
Oh, great, Mark.
So Jeff, thanks for the great talk. I think this is the second time I've heard you give this talk, and it was even better on the second time. So I enjoyed hearing you go through it again. Actually, I want to say, I think one of the aspects that you didn't emphasize, although in fact is implicit in this architecture, which is very valuable, is that you can recool individual atoms, could be the atoms you replaced or any other atom, without affecting other atoms in the circuit in a way that is really very difficult in other elements, because you could take your triplet P0 atom, put it down to the ground state and cool it nicely without affecting any other qubits. And that's actually a very important feature. Thinking about cooling, I would also mention that, I agree with your rough estimates about the impact on cycle time from the atom replacement. There probably has to be some amount of recooling included in that, and that may add to your time budget. But these are details that will be developed and need to be worked out over time. I would just say overall, I find it a very interesting proposal. I'm still trying to find the hole in it that hasn't been discovered yet, but it does look very promising for further study. Let me stop there for now.
Great, thanks, Mark. Great.
Yeah. So can I add a comment? I think this is a really nice work, and also it kind of like comes timely as a kind of a co-design in terms of the hardware and also efficient error correction. And I think what's kind of impressive is just not like you identify the error, but also you kind of engineer and try to convert the error into a really like more favorable erasure error, so that you can actually significantly boost the performance in terms of using more favorable error correction. Yeah. So yeah, really nice readout. Yeah.
Great, thank you, Liang. Ken, it's all yours.
Yeah. Well, Liang took one of my main talking points, but I think the conversion to erasures is amazing, and I think other platforms should take the time to think about how to do it, because I don't think, I think the community is a little bit missed the fact how much better erasures are for error correction if we can, reinitialize and replace. The second thing I'm super excited about is the part with composite pulses. So is a quick, minor correction, which is like the 1 qubit composite pulses we use all the time. The 2 qubit composite pulses and ion traps, yeah, we do suffer from this heating rate. And I think if you could demonstrate the kind of 2 qubit composite pulse, which is like 1 qubit composite pulse related to kind of using type interaction suggested by Jonathan Jones a long time ago, it could be the first system where it actually helps. And I think that in itself would be pretty cool. So should I think that the amount of erasure just goes like time? And do you have a sense of like what the trade-off should be between kind of over rotation angle versus extra erasure?
Yes. Well, first of all, thank you for making that point about 2 qubit gate errors. I was thinking about 2 qubit gate errors, but yes, that's true. The trade-off. So I would think about it this way. So if I was not thinking about erasure conversion and I was just, or types of errors, and I was just generally concerned about the error rate, okay? I could have the situation where I had, let's say 50% of my error came from an over or an under rotation and 50% came from spontaneous decay. And in that case, if what my composite pulse let me do was, suppress my, let's say my error probability is small, so my composite pulse is going to suppress that coherent part basically to 0. But at the expense of doubling the length of my gate. So I now double the spontaneous part. In many contexts, the error probability is the same. The total error probability is the same, so you don't map. But for us, that the first case would basically be described as, let's say, only 50% erasure conversion, because the spontaneous part is only half my total error, and then the other half is just a qubit error. And so I could go from the case of having an error probability, 2p and 50% erasure conversion to 2p and 100% or 98% erasure conversion. That's way more favorable. So I don't know exactly how to quantify that trade, except to say that I think you would almost always want to take it here. There's one other thing about it, which is that actually, when you talk about composite pulses for like trapped ions, you're actually kind of trying to suppress two errors at the same time. One is leakage, and the other is that given that there's no leakage, you have the right fidelity gate. And we have a slightly more relaxed condition here, which is that we can ignore leakage. We can only optimize over the fidelity when you come back, because any leakage just becomes erasure. So we might even be able to have more efficient composite pulse gates than what are possible in other systems because of that.
Yeah, sounds like a great trade-off.
Great. Let me just ask something more general here. So again, going back to a very naive view of or maybe a either layperson or a theorist view of where errors come from, and this very general argument that's made that it's if you had isolated qubits, you can make them almost perfect, but as soon as you start interacting with them, which is what you need to do for gates, you must have, that's where errors start creeping in, and you must have recurrence rates. So let me just try to see, ask you, Jeff, as well as the panel, in general. So in view of this talk, is it I'm trying to see how to update my thinking about this. So here's one thought that I have, which is, okay, so single qubit gates are always, much more reliable than 2-qubit gates, and and this argument that, well, if you want to implement gates, you have to control from the outside, and therefore there'll inevitably be errors. It seems to apply equally to single qubit and 2-qubit gates. So are you, is one way to think about what you're saying, is if we were to extrapolate it, is it an argument saying, look, there's no reason why 2-qubit gates shouldn't be as good as single qubit gates? And maybe this argument that one usually thinks of in the abstract, it really applies to just controlling stuff, but maybe when you have 2 qubits interacting with each other, well, in your case, it's it's through the Rydberg blockade, and maybe that doesn't introduce errors. It's just a metastable state, and you can, by converting it into erasures, you can sort of get rid of those errors or make them much more tractable. So is this could one formulate this as a more general principle, and is there hope that we can pursue it in many other other settings? If you have comments, or anybody else on the panel, I'm just trying to understand how I should think about this more generally.
So maybe I can say something here. So first, it's a question, just look at the history. Single qubit gates have been done already for 60 years, 80 years, or even longer. Yes. Whether it's 2-qubit gates took much longer. So there must be a reason for that. And so now one can analyze what is the reason. And I guess that there are different aspects. One aspect could be that if you want to do a single qubit gate, you use what we would call a classical field to interact with it. So this is this laser field, microwave field, which is full of photons, right? So it's not acting a single system with a single quantum system. It's one single system with a huge quantum system that has very little fluctuations, basically classical. Whereas when we want to do 2-qubit gates, they will have to act one system which is quantum with another system that is quantum, and then it's much weaker, the interaction. And I don't know, that could be one way of looking at it, but I'm sure that there are other ways of looking at that.
And so, sorry, Ignacio, still following up on that. So now, when you have something like this Rydberg blockade, should I think of the moral of the story as saying, well, that's pretty reliable in itself. The noise really comes from other sources, and maybe that's not inherent, or you know, what's the takeaway? I mean, is there another step beyond that?
Well, I don't know. I guess there are many ways of seeing it. But if you have a single atom and you put a huge electric field and you make it rotate, I mean, something will happen. You will do gates with that. And now the idea is that you have to do it with another atom, and you have to create a huge electric field. What you do is that you put it in the requisite state, you put it very close, and then it's a huge electric field as if it was an external one. And this mimics a little bit this other situation, and that's why it's very fast and kind of robust.
Maybe I can add a comment. Actually, I think Jeff mentioned this right at the beginning of his talk, that the way that 2-qubit gates are done with neutral atoms or trapped ion qubits involves taking the physical system out of the qubit space, out of the computational space, and coupling it to some other degrees of freedom that are not entirely stable. So either to the motional state, where we have more susceptibility to noise in the case of ions, or to these Rydberg states that have a finite lifetime with respect to spontaneous decay. And it's that finite lifetime that leads to errors in these systems. And so, I mean, I think it's because of this, it's intrinsically more difficult, and certainly the history bears this out, that it's harder to perform 2-qubit gates with low errors than it is 1-qubit gates. But I would not characterize that difficulty as fundamental. I mean, I think there's an opportunity and a path forwards where the 2-qubit fidelities can be as high or higher than the 1-qubit fidelities that we see today. But there's more work that needs to be done. There's more engineering. I mean, there's also other ideas, for example, utilizing these very long-lived Rydberg states, the circular states that the Roach group has pioneered, and Jeff also has a nice paper on. There's other papers also, which allow you to take advantage of the strong interactions of these Rydberg states while reducing the decay rates by orders of magnitude. So there's a path there to, at least on paper, get to 10 to the minus 5, 10 to the minus 6 2-qubit gate errors. So it's going to be hard, but you know, certainly there's a direction one can explore.
I want to connect to a different part of Umesh's question, which in terms of like the theory world versus the real world. I think one really nice thing about Jeff's work is that and then actually Liang Jiang doing similar work on other error models, is that error has structure. And so normally in these most quantum error correction papers for a long time, people were like, oh, we don't know anything about the errors. We just randomly select them from the poly group on support over the weight of the operation. And that's a great thing to do if you don't know anything. But actually, any real 2-qubit gate, single qubit gate, the errors have a lot of structure. And I think it's been really nice in the last, I'd say the last 5 years, seeing control theorists and experimentalists work with error correction theorists to actually make better codes based on that structure. And I actually think there'll be a lot more work along that direction in the next couple of years.
So following up on that, Ken, so are there already very general principles emerging, or is this still in process? Where would you characterize that work? How would you give the big picture?
I would say I would say it's still in process. I mean, I think erasure errors is a good, like, new thing. Like, oh yeah, we had all erasure errors was good. To me, the one question that Jeff's paper answered for me was like, what fraction of erasure errors do I need to have some gain? And it turns out that gives you kind of a sense of when it pays off or not. In this work, unrelated work with like CAT codes with errors, that gate transparent errors, that's really neat because you can think about basically making almost classical codes where the nodes are so biased one way or the other. But I think what's missing is, anyway, this is just my goofy example, which is, what if your error model was you just drop gates? Like occasionally you just don't apply the gate. I can make a normal error correction code that fixes poly errors that fixes that error, but I don't actually have the tools to make a code I don't have the tools to make a code based on that idea. And I think if we could start to make tools that were not us making poly errors and then finding the right match to the physical errors, but actually based on the physical errors itself, it'd be quite nice.
I see.
Yeah, so can I also maybe add a related comment is that I think that in Jeff's system, what's interesting is that there exists a very clean QND measurement to detect erasure error without causing a significant any damage to the remaining system, which of course still need to be experimentally demonstrated, but it seems like really promising that basically you have all the other different colors of laser to detect those states without compromising the other system, which at least in some of the earlier work in superconducting circuits, usually when you measure something, it will have T1 induced decay and so on. So the system start to collapse, like decay faster. But if what kind of like this in this system, you can kind of detect those erasure error without causing much damage, it's actually a very efficient way to extract the entropy from the system, which is really nice to actually for the control and the error correction. Yeah.
Yeah, I'll ask one other question, which I guess going back to these what you mentioned with the bias preserving gates and so on. So is it the case that with erasure errors that okay, so let me first say my understanding. My understanding was that you need the bias preserving gates to make sure that when you're doing this recursive error correction or something like that, when you concatenate and so on, that you end up getting those biased errors again, right, at the next level. So if you were doing the same thing with erasures, do you need now erasure preserving gates, or how would you see this work? Have we thought through this?
I mean, what I'm about to say might be very naive, but the way I think about bias preserving gates is really that it's natural that like a ZZ gate, that Z errors commute with the gate. So if you have a Z error during the gate, it's going to be a Z error at the end. But that's not true for controlled X, for example. So but you can make it controlled X out of Z gates. But now you have Hadamard's that flip X to Z errors. And so the thing about erasure errors is it's just you just highlight a qubit. And say this qubit has an error, and then you can track that through gates. It doesn't. It's not like that error magically pops up on another qubit. You can track the spread, even if you wait a while before you detect. You can track an error here, it turns into errors on these qubits. So it just kind of goes through gates in a pretty natural way. If you had an error before a gate, you still have an error after a gate.
I see. Okay, great.
Well, can I add a comment to that? I think that in principle, there's still some related discussion about how to do fault tolerance, even in the presence of erasure errors, right? Because in principle, when you have an ancilla measure, some like a syndromes associated with the erasure error, you might still propagate those erasure error to some other like coupled qubits. And there's also some like work related if you can use flat qubits or other better designs to make sure that they still do the error correction fault tolerantly. And I guess that probably here it's maybe you have a mixture of erasure and the depolarization error, maybe depending on the fraction of these different types of error. Maybe you may want to optimize different codes and circuit designs to get a better performance in terms of hardware efficiency and thresholds. Yeah, which I think it's probably related to Steve Flamier's question that are there better codes compared to the XZX code, which are maybe better fitted for this kind of different ratios of erasure and the depolarization error. And yeah, I think that actually will be something interesting also to look into for theorists, especially. Yeah.
I'm so glad you brought up flag qubits, because I wanted to ask if you or somebody else wants to talk about. It seems like there you are trying to with flag qubits also move towards erasures, right? So it would be interesting to sort of speak about these two, and can you say something more general about that?
Yeah, so recently we had a paper on the correcting again another type of erasure error, which is about like superconducting circuits. There's this cosmic ray events, which you can think of as an entire coding block has an erasure. But the way to solve this is to have a next level of coding and connecting different chips. And once you detect erasure, you can use a second level of coding to correct that erasure error. And then there was some discussion, at least in our paper, we also think about using flat qubits to suppress them. But okay, it's just as a beginning because we only consider the erasure error, but in practice, there could be a combination of erasure and other gate errors. Maybe they are more efficient or general design to correct those. But that's only, okay, a little bit part that we're thinking so far, but maybe they are more general. Maybe can add more comments on this one too. Yeah.
Yeah, well, I think well, okay, so at first glance, why is erasure seems terrible, like you've totally lost your qubit. But what separates it from, say, like a leakage type error, where you've also totally lost your qubit, is that you know where it occurred, right? And so flag qubits, in some sense, that's what they do, is they let you know which set of C naughts had a 2-qubit gate error, right? And so unfortunately, in the flag qubit scheme, you can't actually check everything. It doesn't work out. But it's somewhere between like erasure. I think that's a nice way to think about it. It's kind of between erasure and the other way, because we at least have scoped it down to a narrow region of errors.
Yeah, maybe a related comment is that maybe during error correction, one could do it adaptively. Depending on what you see, you will decide what to do next. Then the kind of the flag qubit schemes will have this kind of in the design, and so that will probably give a more efficient like a strategy in correcting errors. Yeah.
That's very interesting. I hadn't thought about flag qubits as being, you know, in between erasures and other things, but I think I kind of thought about other maybe like less efficient schemes for detecting erasures or for detecting atoms that have leaked, where maybe you have to use some additional qubits. And what I wondered about those is how you would characterize, you know, this spectrum from depolarizing errors to erasures. And do you know, because with erasures you have this like higher distance, right? And the steeper slope. So do you know where like flag qubits fall on that spectrum? Like do you get a larger effective code distance or not?
There it's, I think, a little bit orthogonal, because the erasure helps you even if you have like a code capacity model of errors from just sending information through a channel. And flag qubits just makes sense when you're like building the gadgets to look for parity checks. So it's a little bit, yeah, it's not quite apples to apples there. Yeah. But I do think the thing which is important is that the decoder side of an error correcting code, the more information it has, the better it can do. And so erasure is an example where it has a lot of information. Flags give us more information than not using flags. And then I would say that's kind of the things in between. So like if I have, if I have some extra promises on my errors for some reason, I can actually, in my decoder, use that to make the threshold better.
Yeah, maybe to Jeff's question, I think it's maybe more related to like a code design, like rather than just using surface code, which indeed like it can correct up to 50% erasure. But maybe when it's kind of having a relatively high erasure, maybe there are other codes which can also do something quite well, like a quantum polynomial code or other codes. So, but then maybe there's a trade-off between what kind of code that you want to do with the minimum physical resource overhead. And also practically, there's also a question about the connectivity of the hardware, like how to kind of find the code which matches best with the hardware design. Yeah. Because I think for the code atoms case, it's probably you're less constrained with the nearest neighbor coupling, which I think is a great opportunity to look for like a not just nearest neighbor coupling codes, which maybe you can have even like a more favorable like a resource overhead for error correction.
Great. Shall we see if there are any questions from the audience? Let's see. I thought somebody. Maybe if you have, could you raise your hand if you have a. Okay.
I see there was an interesting question from Rob Cook about the ions interacting with the Ripper states.
Okay, so Rob, could you ask the question directly? Okay, well, let me read it out then. It says, Jeff mentioned that two ytterbium ions induce immediate loss. I'm curious if there's any interesting collisional physics between the Rydberg states and the free ions and or photoelectrons. I'm guessing this isn't that much of an issue, else you would add a background electric fields.
Yeah, that's an interesting question. The one we consider this a little bit in the supplement to our paper. We thought about it some more, but the one thing that is close to being a problem but isn't quite a problem is that when you create this ytterbium plus ion, it's got all these ground state atoms around it in this array, and actually this ion is not stopped. It has a small initial velocity because it gets the recoil momentum from the electron that you kicked off. So now it's moving at like 3.5 meters per second, and as it's moving. If it's moving in the plane of the array, it could come and go by one of the other tweezers, and then the question is it gonna get captured there? Because actually the kind of the scattering cross section for an ion ground state atom is not that small. And this is one of these things that just turns out that ytterbium is in this kind of Goldilocks zone, where if this ion was going very much faster, we wouldn't even be able to detect it before it moved too far. And that would be the case for strontium, which has a similar recoil energy, but is half the mass. But if it was going slower, it turns out this capture cross section for the neutral atom and the ion is strongly velocity dependent. And if this ion was going just a little bit slower, then it would actually have a pretty high probability of colliding with this neutral atom. So this 3.5 meters per second is kind of like magical, where it's going fast enough, it's not really going to collide. That collision probability is like 10 to the minus 5 or something like that. So, below where it matters. But it's still slow enough that we can detect it.
Perhaps I could follow up on that. This question is deep in the atomic physics weeds, but let me ask Jeff anyway. So if I have this ion going past from detecting an erasure error, if there's any vector shift of the triplet P0 or vector polarizability of the triplet P0 qubit states, I might dephase a bunch of qubits in the array.
Yeah, I didn't consider that. I can check it. My intuition is that Junie and those guys are doing, well, not with Strontium, but Andrew Ludlow's doing stuff at the 10 to the minus 20 level with these qubits in ytterbium. This is really, my guess is that it's not only not going to not matter, but by like 10 orders of magnitude. But it's worth checking. It's worth checking.
Well, excellent. So I think this probably brings us to the end of the time we have today. So let's see. Jeff, thanks again for a wonderful talk. And thanks to all the panelists for a really great discussion. This was most enjoyable. So I should say that next week is our last colloquium of the spring. It's Lenny Susskind, who will talk about quantum gravity and the quantum extended chair Turing thesis. So see you next week, and thanks everybody again.
Thank you.
Thank you all very much.
Bye.